we have a set of data, y versus t data, we can take the points, there would be numbers here, we can take the numbers and we can plot them as points on a graph. There might be a lot of them. Now, if you think those points indicate something that's actually represented by a straight line, but there are some errors in your observations and so forth, or uncertainties, or whatever, then you can say, okay, well, maybe we ought to draw a straight line that fits that data. And of course, that would be a regression line, or an approximate regression line. So if we do that, then we can estimate the slope in the y-intercept, and your model is y equals mx plus b. Now maybe you think that that really isn't linear, because that straight line there, it looks like this thing might dip a little bit in the middle. So let's say we think actually that maybe the curve isn't quite a straight line, maybe it's more like this. Probably not with the points that I drew, but could be. Okay, so is this the best curve? Okay, well, if it's a curve, then we test it to see if it's an exponential, a power function, or maybe a quadratic function. So maybe it's exponential, maybe a power function, maybe a quadratic function. Well, to test for exponential or power function, what we can do is we can estimate the coordinates of 2 points on that curve. Not data points, but points on the curve. So we take 2 typical data points. Let's just say we take this point and this point. And we estimate the x and y coordinates of each point. And then we plug those x and y coordinates into the form of an exponential function. Or, if we think it's a power function, maybe we plug the coordinates into the form of a power function. So, exponential function would be y equals ab to the t, or y equals ae to the kt. Well, if we plug the coordinates of one point in and then plug the coordinates of another point in to this form, we're going to get two equations. Okay, so we could get, for example, if this point is -1, 3, and this point is 6, 5, then if we plug -1 and 3 into this, well, 3 is the y-coordinate, so y would be 3. And then that's a times b to the t. T is -1. If it's this form, it would be 3 equals a e to the k times -1. If it's, okay, then if we use this point, we can get another equation. Y is 5, x is 6, t is 6. So we have 5 here, 6 here. We have 6 equals a times b to the 5th. Over here, we would have 6 equals a times e to the k times 5. Well, these are just simultaneous equations. We can use methods of solution of simultaneous equations. In this case, we could solve for A and then plug the result in for A down here. We get an equation that we can solve for B, and then we come back and solve for A. It's very easily done. If we're doing it with this form, we can again solve for A. A would be, well, you can do it. It would be 3e to the k, but you'd have to do a little bit of work to see that. But then you plug that in here, simplify it, and solve for k. Of course, k is going to be in the exponents. You're going to have to use a log. You'd use a natural log to solve this equation, but this equation could easily be solved. This equation could easily be solved for a and b. Once you've solved for a and b, you've got your function. Or over here, once you solve for a and k, again, you've got your function. So we can easily fit an exponential function or power function to a curve with 2 points. Now, whether the curve is actually an exponential function or a power function, we'd have to test then by graphing the function and seeing if the graph happens to fit the points. Or maybe we do both functions. Well, we do an exponential function, we do a power function, and see if the graph fits the points. If it's an exponential model, power function model, well, we do the same thing, but the form would be y equals a times x to the t. Sorry, it would not be a times x to the t. It would be a times t to the power. Okay, because you raise your base to a power, you raise your number to a power. Okay, t is not the base, t is now your variable. And of course, if it's a power function, you might want to think of the variable being x. So it'd be a x to the p. That might look a little better that way. Okay, well, then we could have y equals, well, or y equals ax to the p. The point is that a and p are the parameters that we need to solve for. And we can solve for a and p either here or here by plugging in coordinates again. So from the first point, with t equals -1, y would be 3 equals a times -1 to the p. And from the second point, you would have, oh boy, when I wrote this down, I wrote it down wrong. I had the 5 and the 6 mixed up, and I hope that didn't cause you too much distress. Let's fix this. Okay. Y is 5 and t is 6. Okay, so anyhow, if we have this curve and we think maybe it's a power function, then we plug in 5 for y, 6 for x. And we get 5 equals a times 6 to the p. We can then solve the equation for p. We're going to have to use exponents, but you could solve the first equation for a, plug into the second equation, do a little simplification, and then you're going to have to use logarithms to solve for p because it's in the exponent. Okay, the point is, if we have 2 points on a curve, if it's an exponential function, there's the form or there's a form. If it's a power function, it's either this form or this form. Another possibility mentioned, other than the linear, is quadratic. If it's quadratic, our quadratic model would be y equals a t squared plus bt plus c. And we would need 3 points. So we get a third point on the curve. And maybe this point is 2, 4. It's not a very good likeness, but let's just say that point is 2, 4 for illustration. Okay, so y equals 3 when x equals negative 1, so we get 3 equals a times negative 1 quantity squared plus b times negative 1 plus c. Then y is 4 when x is 2, so we get 4 equals a times 2 squared plus b times 2 plus c. And here we would get y equals 5 when x equals 6. And there we have 3 equations with unknowns a, b, and c. We solve them using the methods for solving 3 equations, 3 simultaneous equations. We could rewrite these equations by doing the arithmetic here and flipping sides. We would get a minus b plus c equals 3 from this equation, just doing the arithmetic. Here we get 4a and 2b and c, so it's 4a plus 2b plus c equals 4. And here it's a times 6 squared, that would be 36a plus 6b plus c equals 5. Well, those equations would not be particularly difficult to solve. I would recommend starting by eliminating c. The point is, if we've got a curve, if we want to fit an exponential model, we use this form or this form. We take the coordinates of 2 points, we plug them in. Power function, same thing except this form or this form. Quadratic function, this form. We get, in any case, a set of simultaneous equations. This set, if we use the a, b to the t model for the exponential. This set of equations, if we use a, e to the kt. This set of equations, if we use a, t to the p, or if it was y versus x, it'd be a, x to the p, power function. And if it's a quadratic model, we do this. If it's a linear model, we could also use the form y equals mx plus b, and we could plug the y and the x coordinates in here. We get 2 simultaneous equations in the unknowns m and b. We could solve for m and b. An alternative way of doing that, okay? So it's kind of an important idea. And there's another way of fitting exponential and power functions, and that's to do the log y versus x graph, linearize it, and solve the equation. And you can do the same thing with a power function model. I'll demonstrate that quickly in, let's see how long we're going here, 13 minutes. I'm going to go ahead and do that in this same video. Okay, so if we've got y versus t or y versus x, we've got numbers here, and that gives us a graph. But the first thing we do is we do, and it's y versus t has t here and y here. I saw some work where somebody had reversed those two, and now I'm starting to reverse them. Of course, I know better, but okay, so this is y versus t. Log y versus t has t here and log y here. And there's also another one we could do. Your text doesn't do it. but there might be problems in the final where you need to, and it's done very similarly. Okay, so you fill in the t, same as they are here, and you fill in the log of y. You take the logs of all these. Could be your base 10 log, use your log key in your calculator. Could be natural log, it's not going to matter. Okay, over here, you do the same thing, except you do log t. So you do log y versus log t. Now, if this graph is linear, as I estimate, you can't estimate till you graph it. You graph it and estimate the slope m, the y-intercept b. So your graph might look something like this. It looks like a straight line. You draw the straight line. Here's your y-intercept. And your slope is rise over run. So just find the rise, divide by the run, and you have your slope. And then you can say, okay, the graph is log y versus t. This is log y. This is t. And you can say that log y equals m times t plus b, or mx plus b if this happens to be x. And you can solve for y. And you should know how to solve the equation log y equals mt plus b for y. If it's an log log, you do 10 to the log y, that gives you y. You do 10 to the mt plus b, and then simplify it. Okay, if this is linear, you do the same thing, but this time it's log of y versus log of t. And your graph, whatever it is, okay, your points from this table could give you a straight line. Okay, now, one thing I'll back up and say, if this is a straight line, then this isn't a straight line. If this is a straight line, this isn't a straight line. Okay, you might think about that. So, if this is a straight line graph, you just do your y equals mt plus b, and you'd be done. Okay, so anyhow, if this graph is linear, well, it's just like it is here. You're going to have a b here, and you're going to have a slope. And m is rise over run. And now you're going to have log y equals log t plus b. Because this, well, it's like y equals mx plus b, but it's log y, not y, and it's log t, not x. Okay, and I didn't include my slope. Let me fix it. When you solve for y and simplify, you get your function, you get your model. Okay, so two ways to get the model. If you have a data set, you can linearize as was done in the last section of Chapter 4. You could linearize the log y versus t. If log y versus t gives you a linear, then you've linearized. If it doesn't, then maybe you try log y versus log t. And if that gives you a straight line, you do this. If neither one of them gives you a straight line, maybe you try a quadratic model. Maybe you try something else. It'll be fairly simple in this course. Any model is either going to be linear, quadratic, exponential, or power function. So, once more, given a set of data, you can draw the graph. If it's a straight line, estimate the slope and the intercept, and you get the equation. If it's a curve, then it might be exponential, it might be a power function, it might be quadratic. You can use simultaneous equations to test an exponential function or a power function. You can use a quadratic model. Whichever model fits the data best, fits your data curve best, is the model you're probably going to use. Okay, questions are always welcome.